Record. Now we are recording on the computer. I had forgotten to hit the record button. So I'll just kind of repeat a little bit of what I said before, but just a little bit faster. Last week and the week before, we looked at Unit 1, and we covered wavelength, frequency, and speed of sound. That's one dimension of sound, is frequency. Now we're going to turn our attention to the intensity, the amplitude of sound. And intensity isn't measured in hertz, as like frequency. Intensity is measured in decibels. And the decibel is little d, big B, opposite of hertz, which is big H, small z. Okay? So, the decibel, invented by Alexander Graham Bell, who invented the telephone. A decibel is a tenth of a bell. Deci means tenth. Okay? At any rate, let's go and take a peek at our screen, and we'll take a look at our notes and what we'll try and cover. We're gonna spend 2 weeks on this particular unit. So let's get to our notes. Here we are. Intensity, decibels, power versus pressure. I hope you all have this printed up ahead of time so you can follow this in the Zoom session. If you don't, I would pause the Zoom session, print it up, and then come back. It's essential. Look at number 1. In physical, not perception, not psychoacoustical terms, that's what we look at after our midterm. Right now we're still in the physics of sound. The physics of sound is all pre-midterm, okay? In physics, or the physical terms, intensity is completely independent from frequency. On a waveform, number 2, on sound waves, intensity is represented by the amplitude, the height. How tall is the sound wave? Okay, intensity is measured in decibels. Back to number 2 here, though. Intensity, remember, frequency is the number of bumps you see per second. Intensity has nothing to do with that. It's the height of the bumps that you see. All right, intensity is measured in decibels. And first, let's look at some terms relating to intensity. Here we go. And I'll say again, FNO, freak not out. Check this out. Force equals energy. And it's measured in units of dynes or newtons or pascals. Okay, those are units of force. When you look at pressure, this is very important. Put a star by this one. Pressure is force over an area. Force over an area. And so, to stop sharing and look at the screens again, your hand against your face, your finger against your face. Okay? If you push hard against your hand, you've got force over a big area, not much pressure. If you have a lot of force against your fingertip, you feel it more. That's because the same amount of force is directed over a smaller area. So, F over A, pressure equals force over area. Okay, very important. It kind of relates to the middle ear in anatomy, doesn't it? Okay, now we're looking at it sheerly in terms of physics of sound. And sound amplitude is measured in sound pressure level. So many times you're going to encounter the terms dB, SPL. dB, sound pressure level. What's the pressure of the sound against your eardrum? Okay, that's how they measure the amplitude of sound. That's how they began measuring sound amplitude. What was the pressure against your eardrum regarding a sound? dB, dBSPL. All right, back to share screen again. Okay, read with me. Pressure is measured in units of dynes, again, or pascals or newtons per centimeter squared, per square centimeter. Okay, force over an area per square centimeter. What's a square centimeter? About the size of a sugar cube. Okay, it's the one side of a sugar cube. What's a square centimeter? take a look at your finger and aim your finger at yourself. That's a square centimeter. The tip of my finger. Okay? So pressure is force over an area, and the area we are concerned about is a square centimeter. There we go. We'll get our ducks in a row here. Power is another thing, because you can also measure sound in terms of power if you wanted to. Power is different from pressure. Okay, so you can measure sound intensity in terms of its pressure, or you can measure sound intensity in terms of its power. Now, what's power? Power is work done. Okay, pressure is force over an area. Power is the amount of work done. All right. And power is expressed in watts per centimeter squared. How many watts is your light bulb? Okay, that's a power unit. What's the power of the electricity? Is it a 100-watt bulb, a 60-watt bulb? Watt is a unit of work done. It's a unit of power. Okay, watts represent work done as per some unit of time. Watts equals pressure times velocity. Don't freak, just leave it. Okay, here's what you got to put a star by. Intensity of sound can be measured either in terms of pressure or in terms of power. We choose to measure sound mainly in terms of pressure. You know why? Because the ear works like a pressure device. The ear receives sound. The ear isn't working. The ear isn't a speaker. The ear is a receiver. Okay, if we were talking about a speaker, we'd really want to be talking more in terms of power because it's producing sound. But the ear receives sound. So even though you can measure sound in terms of its power or in terms of its pressure, we choose pressure A because the ear is a receiving device. There's another reason why we talk about pressure instead of power. A second reason. The second reason is pressure is easier to figure out. Power is a more difficult mathematical calculation. Pressure is easier. So we use pressure for two reasons. One, because it's easier, and secondly, because the ear works as a pressure device. Back to the screen. Here we go. Sound, power, let's get it out of the way. Let's dispense with power, but let's look at it quickly and then we'll put it in the rear view mirror, okay? Power looks at what's produced in terms of what work was done. And work is measured in joules, and 1 joule per second equals 1 watt, usually 1 unit for sound, blah, 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 blah. Don't worry about it, leave it alone. Here's what you got to look at. And then we'll look at it in terms of pressure too. What they did, read what's grayed out there. Have a look at it. Power required in terms for a human to hear a 1,000 hertz tone at 1 meter distance from a speaker with 2 ears. Note the 3 conditions. One is the frequency, 1,000 hertz. Another one is the distance at 1 meter. And the second one is the condition, 2 ears. What's the softest power? Okay, that's what researchers cared about at the beginning. In the early 1900s, when people started to play around with this, they asked themselves, they said, self, what's the softest power that a human being can detect of sound? What's the softest sound power that a human being can detect? And then someone said, well, what frequency? Let's just pick 1,000. How come? It's in the middle. It's a nice round number. Let's use 1,000. Because when we test hearing, we test from 125 hertz, 250, remember this? 500, 1,000, 2,000, 4,000, and 8,000. Remember, those are all octaves, aren't they? When you double the frequency, you go up 1 octave. So the audiogram test, the paper test upon which we test hearing, has 7 octave frequencies. 125, which is actually low C on a piano, 250, which is actually middle C in music, 500 hertz, which is actually high C in music, and then 1,000, 2,000, 4, and 8. Every time you double the frequency, you go up an octave. Recall and remember. Good. So let's pick 1,000, because in the audiogram of human hearing, it's in the middle. And it's a nice round number. Okay, Jose, what's the softest it takes for a human being with normal hearing to just barely hear a 1,000 hertz tone at 1 meter distance from a speaker with 2 ears? Okay, because remember, 2 ears are better than 1. Okay, and we'll go into that more later on, but 2 ears are better than 1. So you're listening with both ears, and you're not wearing headphones. You're in front of a speaker, and how far are you away from it? 39 inches, because that's a meter. And what frequency are you talking about? 1,000 hertz. Remember those 3 conditions, okay? Well, those 3 things. Now you're looking, what's the softest power required to just barely hear that? All right, what does it say in our notes? Yikes. The softest power required to just barely hear is 10 to the minus 16 watts per centimeter squared. What the Sam Hill is that? Let's look at it. That is small. That's a 1 with 15 zeros in front of it and a decimal. That's like going 0.000, comma, 000, comma, 000, comma, 000, comma, 0001. That's about a trillionth of a watt. Okay? A trillionth. So let's look at what a trillion is. Let's make sure we've got our numbers right. 1,000 has 3 zeros behind the 1, doesn't it? 1,000,000 has 6 zeros behind the 1, or after the 1. 1,000,000,000 has 9, and a trillion has 12. Okay, you got lots. 10 to the minus 16. You're talking a whole bunch of zeros. Okay, so back to our notes. What's the softest it takes to just barely hear a 1,000 hertz tone at 1 meter distance from a speaker with 2 ears? In terms of power, it's 10 to the minus 16. And in terms of power, what's the loudest sound you can tolerate before it hurts? Well, crank up the intensity of that 1,000 hertz tone, buddy. Crank it up, make it louder, and as loud as a person can generally tolerate it. Stop. Okay, what's that power? That's 10 to the minus 4 watts per centimeter squared. So what's the difference between 10 to the minus 6 and 10 to the minus 4? What's the difference? Heck, I'm no mathematician. I'm not going to sit and calculate that. I'll just tell you what the difference is. 10 to the minus 4 versus 10 to the minus 16. What's the difference between 4 and 16? 16 minus 4 is 12. So the difference between 10 to the minus 16 and 10 to the minus 4 watts per centimeter squared is 10 to the 12 minus, or watts per centimeter squared. What is that in terms of a number? What the heck is 10 to the 12? 10 to the 12th power. 10 with a little 12 on the top. What is that? That's a trillion. That is a 1 with 12 zeros behind it. 1,000 has 3 zeros. 1, 000. 1,000,000 has 6, 1, 000, 000. 1,000,000,000 has 9, 1, 000, 000, and a trillion has 12. Okay, 1, 000, 000, 000, 000. Well, you think I'm getting tongue-tied here, okay? A trillion is a lot. So let's talk about this in English. The loudest sound you can tolerate has 1 trillion times as much power as the softest sound you can just barely hear. The loudest power you can tolerate of sound has 1,000,000,000 times as much power as the softest sound you can just barely hear. There you go. Now, do you think in a hearing test we want to sit there dealing with increments of 1,000,000,000,000? Do we really want to say that someone's hearing is 9,412,000,000, blah, 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 and then someone else's hearing is, you got way too many increments in there. So we can't deal with that in human hearing testing. I mean, let's face it, how many frequencies do we test? 7. We can deal with 7. 125, 250, 500, 1,000, 2,000, 4,000, 8,000, cool, 7. But in terms of intensity, when you're measuring how loud do you have to make those tones for the person to just barely hear, remember, you're going to be in clinic. You're going to be testing someone's hearing. And you're going to be measuring how intense did you need to make the sound for the person to just barely hear. Well, we just saw in terms of power, that's ridiculous. You've got 1,000,000,000,000 increments. So the softest you can hear compared to the loudest you can tolerate, you've got 1,000,000,000,000 increments in there. That's like a thermometer with 1,000,000,000,000 little marks going from the top to the bottom. Insane. So we can't do it. We have to figure out something else. Back to our notes. So you have it right here where I'm graying out. 10 to the minus 16 is 1,000,000,000,000 times larger than 10 to the minus 4. So the range of our hearing in power units is 1,000,000,000,000 to 1. Let's leave power alone and go to sound pressure instead. Let's look at pressure. Let's do pressure instead. Forget the power of the sound. What was the pressure against the eardrum? When the guy's listening to a 1,000 hertz tone at 1 meter distance from a speaker with 2 ears. Remember, the same listening condition. Only now you're not measuring what's the greatest and what's the softest power. Now you're looking at what's the greatest and softest pressure. Okay? So first let's look at the softest. Pressure looks at what's received on a diaphragm, like a microphone, like your eardrum. And the common unit for pressure is dynes per centimeter squared. Remember that. Put a circle around it, put a star by it. Power is watts per centimeter squared. Pressure is dynes per centimeter squared. Power, the range is 1,000,000,000 to 1. Pressure is different. Okay, let's look at pressure now. Here you have some person sitting in front of a speaker, and the person's listening to a 1,000 hertz tone at 1 meter distance from a speaker with 2 ears, and you're measuring the pressure against the eardrum. You turn it down, 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 till the guy can't hear it anymore. Now here, right where I'm graying out, don't worry about it. Just leave it, okay? Don't think about that at all, okay? Just think about what I'm saying. And actually, let's just jump down to here. Reference for sound intensity in sound pressure level, not intensity level, not power. Okay, power deals with IL. Power always talks about dBIL, dB intensity level. Okay, pressure talks about dB sound pressure level. So let's look at dB SPL. And what's the softest dB SPL? Look what I'm graying out here. The smallest pressure required for a human to hear a 1,000, get rid of this power here, take that out and go, get it out, okay? That's the softest pressure required for a human to hear a 1,000 hertz tone at 1 meter distance from a speaker with 2 ears. And the smallest pressure, put a circle around it, 0.0002 dynes per centimeter squared. 0.0002 dynes per centimeter squared. I didn't make it up. That's what it is. And you can tell it's pretty soft as well, can't you? Okay? So 0.0002 dynes per centimeter squared ain't much pressure. But at least, okay, keep going with me. What's the largest sound pressure that you can tolerate. Let's do the same thing. Let's crank it up, crank it up, crank it up, crank it up until it hurts. And you'll find out that the loudest pressure, or the largest pressure humans can generally tolerate, is about 200 dynes per centimeter squared, about 200. Okay, so what's the range between 0.0002 and 200? What's that range? Let's figure that out in terms of math or arithmetic again. So let's do it. And I'm going to show you a picture. And the picture I'm going to show you is here. Okay, look at the graph. Look at the picture. You got to read graphs in this field because hearing aids are often read on graphs. So let's talk turkey here, okay? 0.0002 dynes per centimeter squared. They called that 0 decibels, SPL. And if the pressure was increased by tenfold, now look at, you got one less zero, okay? Now you're at 0.002. 0.002 has 10 times as much pressure as 0.0002 does. So when the sound pressure against the guy's eardrum was 0.002 dynes per centimeter squared, they called that 20 decibels, SPL. And when the sound pressure was 0.02 dynes per centimeter squared against the guy's eardrum, they called that 40. Do you see the trend here? Every time you increase the pressure by a factor of 10, you go up 20 decibels. So by the time you're at 200 dynes per centimeter squared, look where you are in decibels, 120. Now, we can deal with 120. 120 is cool. I mean, okay, what's the range of your hearing? 80 decibels, 60 decibels? Well, how loud did I need to make the tone for you to just barely hear it? Could you hear it all the way down to 0? Or did I need to turn it up to 20? Or did I need to turn it up to 40? Or 60? Or 80? 100? Or 120? Okay, I can deal with a range of 120. But please remember, really, the range is 1,000,000. Watch this. 10 times 10 is 100, times 10 is 1,000, times 10 is 10,000, times 10 is 100,000, times 10 is 1,000,000. Let's do that again. This times 10 is 10, times 10 is 100, times 10 is 1,000, 10,000, 100,000, 1,000,000. So in terms of pressure, the range is 1,000,000 to 1. Okay? In terms of power, the range is 1,000,000,000,000 to 1. So we can think about it like this. The softest you can just barely hear is the softest you can barely hear. You can call that what was the power, or you can call that in terms of pressure. And the loudest you could tolerate, the ceiling, the loudest sound you could tolerate, you could talk about that in terms of power, or you could talk about that in terms of pressure. And if you're talking about that in terms of power, the range is 1,000,000 to 1. Bottom hand, top hand. Now let's move to pressure. Look at my hands didn't get further apart. The softest you can just barely hear is the softest you can just barely hear. The loudest you could tolerate is the loudest you could tolerate. But here I'm talking in terms of pressure. Here I'm talking in terms of power. They're just two different languages. One's Polish, one's German. Okay? Think about it like this. And this is kind of why I gave you a picture of it in your PowerPoint notes. Let's look at this picture here. You got two thermometers. Okay? And actually, look at the very first picture. The softest you can just barely hear is like a mouse. The loudest you can tolerate is a group of elephants. You see what I'm saying? Like the range of your hearing from softest to loudest is huge. And in terms of power, it's 1,000,000,000 to 1. And in terms of pressure, it's 1,000,000 to 1. But look at our thermometers. Okay? And look at it well. I'm going to just concentrate on this picture. We're going to spend some time on it. What is freezing in the United States? In the US, it's 32 degrees. Okay? And what's boiling in the US? 212 degrees. So here you're looking at, look at this arrow here. Freezing, 32. Boiling, 212. All right. Now, drive your car north and come to where I live in Canada. Okay? Because I'm talking to you from Vancouver, British Columbia, Canada, about 90 miles north of Seattle, Washington. Now, lakes freeze over here too. Okay? But we call freezing 0. And we call boiling 100. Now look, the thermometers are the same length. Okay? Freezing is freezing is freezing. Boiling is boiling is boiling. It's just how I measured the two that are different. Here, I've got a whole bunch of increments. The thermometer, the degrees are skinnier. Okay? Whereas on the left, the thermometer, the degrees are a little bit thicker. The distance between freezing and boiling has 100 units. Whereas in Fahrenheit, the distance between freezing and boiling, you got about 180 increments. Okay? So I'm giving you this as an analogy. Think about this as pressure, and think about this as power. All right? So power has way more increments. How many increments does power have between the softest you could hear, we'll call that freezing, and the loudest you could tolerate, we'll call that boiling. All right? How many increments? 1 trillion. Now let's go over to Celsius, we'll call that pressure. And how many increments are between the softest you could hear versus the loudest you could tolerate? 1 million. Okay? And it's not that the range got smaller, it's just that the increments got bigger. 1 million increments between the softest and the loudest versus 1 trillion increments between the softest and the loudest. One's pressure, one's power. All right? So you get all the verbiage on here. Look at the bottom in terms of, well, look at power first. The softest you could hear was 10 to the minus 16 watts per centimeter squared. We'll call that the freezing. And the loudest you could tolerate was 10 to the minus 4 watts per centimeter squared. And there's 1 million increments between that. Okay? Look what it says here. Okay? 10 to the minus 4 is 10 to the 12 times bigger than 10 to the minus 16. So that's 1 trillion. Count the zeros. Now go left. 200 dynes per centimeter squared is 10 to the 6 larger than 0.0002. And that's 1 million. What is 10 to the 6? 1 million. So it's not that the range got bigger, it's just that the thermometer you used to measure the distance, the decibel distance, the thermometers were different. So now back to your notes. Here you go. Here you go. Look at the very bottom. Power equals pressure squared. 1 trillion equals 1 million times 1 million. Okay? But please remember, the decibel distance didn't change. The softest you could hear versus the loudest you could tolerate remains the same. It's just that in one instance you used power to do that measurement, and in the other instance you used pressure. Okay, read with me here. Largest pressure you could tolerate, 200 dynes per centimeter squared. 200 dynes per centimeter squared is 1 million times bigger than 0.0002 dynes per centimeter squared, but that's still too many units to use to test hearing. I don't feel like going to someone saying, okay, Anna Wood's hearing is 666,928, and Ted Venema's hearing is 812,902. 1 million is still too much. The increment's way too many. Even though it's way less than 1 trillion, it's still way too many. So what do? We make the decibel. We call it the decibel from hell. And this is the graph you gotta remember very, very clearly. This is the one. There's your pressure on the horizontal axis. You've seen this before. We're looking at it again. Dynes per centimeter squared. You've got 1,000,000 increments between the left here at 0.002 and the right at 200. But we use logarithms to change that horizontal axis into the vertical. And by logarithms on base 10, all I mean is the softest it took for a normal hearing human to hear a 1,000 hertz tone at 1 meter distance with 2 ears. What was the softest pressure against the eardrum required to hear that? 0.0002 dynes per centimeter squared, right there. And now you crank up the power or the pressure and turn up the volume, and now the pressure against the eardrum is 200 dynes per centimeter squared. Well, please remember the rule. Every time you increase the pressure by a factor of 10, you've gone up 20. Increase it by 10 more, you've gone up another 20. Increase it by 10 more, you've gone up another 20. So now, by using logarithms, we have been able to change pressure into decibels, which is a nice handy unit because now you've got 120 increments. Okay? 120 increments between the softest you could hear, 0, versus the loudest you could tolerate, 120. And when you look at an audiogram on a hearing test, the audiogram has 7 octave frequencies going across the top, and the decibels running down the side go from 0 to 120. Now, those are numerical units we can handle. And but in your textbook, you will see this picture too. This is in your text, Lass and Woodford. And they're just telling you how logarithms work. 10. Okay, whoa, what the heck did I do? Don't do that, Ted. Anyway, I just moved my whole slide here. Move it back. Okay. Logarithms are simply how many times did the number have to be multiplied by itself to equal that number? Well, 10 times 1 is 10. 100, what's the logarithm of 100? 10 times 10. Okay, that's 10 squared. 10 times 10 times 10 is 10 to the third. That's 1,000. 10 times 10 times 10 times 10 is 10 to the fourth. The logarithm is 4. That's 10 with a little 4. 10,000, and so on, and so on. So 10 to the 6 is 1,000,000. That's 10 multiplied by itself 6 times. Okay? And that's also seen on this picture here. Multiplied by itself 6 times. Keep 2, 3, 4, 5, 6. 5 o'clock, 6 o'clock, rock. 7 o'clock, 8 o'clock. So anyhow, the decibel is based on logarithms. Here you go. dB, little d, big B, is a unit based on logarithms. And it is used to define ratios between powers, pressures, or anything. We choose pressure instead of power because it's easier, and plus because the ear works as a pressure device. Cool. The dB is 1/10 of a bell, named after Alexander Graham Bell. You see, when Alexander Graham Bell tried this stuff, he called this 20, he called it 2 bells, 4 bells, 6, 8, 10, and 12. And later on, people thought, yeah, that's a little bit too coarse. That's not quite fine enough. So let's break it down into tens, 1/10 of a bell. That way the softest you can hear is still 0, but the loudest you can tolerate isn't called 12, it's called 120. We should do that because that provides a little bit more of a finer range upon which to measure someone's hearing intensity. Because someone might hear, hearing at 50 versus 60, well, what about something in between? What about 55? Okay, that's why they did that. So, again, just to be technical there, decibels, look where I'm graying it out, is based on logarithms because they compress a huge range of numbers into a smaller one. Okay? And here you've got to put a star by this here too. Whenever you're looking at ratios, like like we just did in that graph, you always have to define the corner. Let's look at the corner of the graph right here. Okay, that's the softest it takes. And you have to have that ground. That's called the ground. Whenever you're going to be measuring ratios of how intense something is, you have to know what the ground is. Let's face it, if you want to say you're looking at an apartment building and you're looking at a house next to the apartment building, if you want to say the apartment building is twice as tall as the house, you got to know where the ground is, right? You have to define what the ground is. Otherwise, you can't say the apartment building is twice as tall as the house, okay? And the ground is the softest it takes to just barely hear. And in terms of pressure, that is 0.0002 dynes per centimeter squared. And when you convert that to decibels by using logarithms, we'll just call it 0. We'll call that ground 0. So what's the softest pressure it takes against the eardrum to just barely hear a 1,000 hertz tone at 1 meter distance from a speaker with 2 ears? 0.0002 dynes per centimeter squared. That's what the pressure is. And what are we going to call that in decibels? 0. That's our ground. Ground 0. Ooh, nasty thing to say. With apology, this is September 11 when the trade towers were bombed. Please remember that, and we'll all have respect for that awful incident. Anyway, in terms of hearing, the bottom, the ground, is 0 dB SPL. And what is 0 dB SPL in terms of pressure? 0.0002 dynes per centimeter squared. Okay, and we're not talking pressures anymore. We're going to talk decibels. That's what we do. We measure intensity in decibels. And why do we do that? Because it compresses a huge range of pressures into a nice unit of from 0 to 120. It also kind of lines up with your perceptions. 60 sounds about twice as loud as 30. So it kind of works that way too. Okay, and as we pointed out earlier on the bottom here, power equals pressure squared. A trillion equals a million times a million, but that's for nerds only. But that's because you had a trillion increments between 0 and the top in terms of power, that power thermometer, and you had a million increments in terms of the pressure thermometer. And I always like this picture. For me, it helps to spell things out. But at any rate, enough on that. Let's move on to page 2. There you go. All right. Let's kind of slow down here. What are ratios? We talked about ratios, logarithms. Things get kind of weird. But let's look at the top here, this top paragraph. Right there. Okay? And note the word nominal. Note the word ordinal, note the word interval, and note the word ratio. And now we'll just talk. Though there are 4 ways to assign numbers to things. Okay, there's 4 ways. The easiest way is called nominal. Nominal means to name. Okay, you're just like names, like numbers on football jerseys. Numbers on sports players' sweaters. Okay, they're not ordered in any way. It's just, I'm number 5, I'm number 99, I'm number 12. You're just naming with numbers. Nominal. What happens if you start ordering them in terms of height? What happens if you take the players and you organize them in terms of their height? Okay, now you're not only naming, but you're ordering along some dimension. Number 1 is the shortest, maybe. Number 2 is the next shortest. Number 3 is taller. Number 4 is taller. Number 10 is the tallest. Okay, that's ordinal. That's ordering. Now you're assigning numbers according to order along some dimension. Okay? What's the next most complicated? The third way is called interval. Now, interval, interesting. But back to ordinal. Think about a horse race. Win, place, or show. What horse came in first? What horse came in third? What horse came in last? Okay, what if you said, hey, this was the fourth horse to come in on the race. Maybe number 1 came in first, number 2 was neck and neck with number 1, number 3 was just at the tail of horse number 2, and horse number 4 was an entire lap behind. Well, they all came in order, but there wasn't equal distances in the orders, is there? Okay, think about 5 different companies. What's the biggest company? Number 1. What's the second biggest company? Number 2, but it's almost as big as number 1. The third biggest company, almost as big as the second biggest company. The fourth company, way behind, but hey, it's the fourth. Okay, but see how the distances between each item ordered wasn't the same. That can happen with ordinal. So ordinal simply means ranking. When you think about ordinal, think about ranking with numbers. And oftentimes advertisements are very misleading that way. They can say, hey, we're the third largest toothpaste company in the world, or we're the third largest bank in the world. Yeah, well, the first 2 are neck and neck, and you're way, way, way behind. Yeah, but we're the third biggest. Okay? Ranking leaves a lot unsaid. Interval is the third way of ordering according to numbers. And interval is way different. Interval is kind of like, we'll just talk about inches on a ruler. Okay? So you're looking at a ruler, 12 inches long. So 1 inch, 2 inch, 3 inch, 4, 5, 6. Hey, they're ordered. They're named. Secondly, they are ordered. And thirdly, the interval between each inch is the same. Now we're talking turkey. Okay, that's the third way of assigning numbers to things. Interval. And this is important to know in our field and in any field. You know why? That's what surveys tend to do. They take your emotions and your feelings and they plot them on an interval scale. Because when you've got equal distances between each numbered item, they are not only named, they're not only ordered in terms of whatever, they're also the intervals between them are equal. Then you can do something called statistics. So that's why you always get surveys. How did you feel about our bank's services to you today? If you were extremely happy, give a 1. If you're so-so, give a 3. If you hated it, give a 4. If we were somewhat okay, give us a 2. If we were pretty bad but could be worse, give us a 4. Okay, so you've got your 5 different numbers and you're plotting your emotions on those numbers. You loved it. Oh, it was pretty good. Oh, it was okay. I didn't like it very much, but I hated it. Okay, you took someone's emotions and you've plotted them on an interval scale. So now you can take those surveys, stick them into the computer, and do stats. Number crunch. Ta-dum, 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 ta-da-da-dum. Okay, cool. Now let's look at the fourth way of assigning numbers to things, and that is the ratio scale. The ratio scale says not only are you naming, not only are you ordering, not only are the distances equal between each ordered item, but now you've also defined the ground. You've defined 0. Okay, that's what the ratio scale does in addition to the interval scale. So think about temperature. I'm going to go back to these thermometers here and look at temperature. All right, check this out so we can drive this home. Otherwise, it won't make sense to us. Here's 2 thermometers. You can look at Fahrenheit. Let's look at the USA because you guys are in the States. You got 32 degrees. You can go up to 40 degrees. You can go up to 50. You can go up to 60, 70, and so on. Okay, but can you say, is 50 degrees twice as warm as 25 degrees? Not really. 50 degrees is 25 degrees warmer than 25 degrees. But can you say that 50 degrees is twice as warm as 25 degrees? Is 10 degrees twice as warm as 5 degrees? No, you can't say that. Doesn't make any sense. And you know why? Because you haven't defined zero. Only when you have a ground can you talk about the apartment is twice as tall as the house. The ratio scale, so that you can say something as twice as intense as, or 4 times as intense as, or 10 times as intense as. That requires naming things with numbers, not only nominally, ordinally, intervally, but also defining the ground. There you go. That's just a bit of high-level, highfalutin stuff. Here you go. Our number system is based on logarithms of log 10. And that's what you saw in your textbook in this particular picture. Okay? That's how our numeric system is based. Now, in your Martin textbook, I'm not sure if your edition has this awful, awful picture. It's too complicated for me. It's got way too many numbers on it. But basically, I like column F, dB, SPL. And I like this column here. It talks about how many dynes per centimeter squared. That works. Okay, I like that. Though these two columns kind of make sense to me, but enough on that. I like this one better because it's simpler. Okay, it's just talking about how we arrange our numbers on a decimal system that way, based on logarithms of 10, and that's why we could use this to come up with a graph that takes dynes per centimeter squared, and we can transmit that to decibels, sound, pressure, level. How are we doing it? We're doing it by doing this. Okay? That's all I'm saying. Okay. Let's move on down here. We typically measure sound intensity in terms of decibels, sound, pressure, level. And the abbreviation for that is little d, big B, space, capital S, capital P, capital L. And here is your last formula in the class, in this course, to know. Okay? In other words, you remember the first two. Frequency is 1 over the period. Period is 1 over the frequency. That's your first set. What was your next set? Wavelength is speed over the frequency. Okay, frequency is speed of sound over the wavelength. Wavelength is speed of sound over frequency. Frequency is speed of sound over wavelength. That was your second set of formulas that we covered in Unit 1. Your last one is this one. Here we go. dB SPL. Share screen. dB SPL. Go to here. dB SPL equals 20 times the logarithm of some sound pressure over the reference sound pressure. There it is. Look at the top line. It has 3 things. A 20, and then it has logarithm, and then it has some sound pressure. Okay, and some sound pressure over the bottom. There's a numerator and a denominator there, a top number and a bottom number. So looking from the left first, this here first, that's the ratio. Notice what the bottom number is. It's always 0.0002. Always, always. That's the ground. That never changes. So the bottom number never changes. Okay. And then the second part of this formula, look at this word called log. That's the logarithm of the ratio. Here's the ratio. Once you've figured out what the ratio is it 10 to 1? Is it 100 to 1? What is it? You know, what's the ratio? Okay. Then you find out what the logarithm of that ratio is, and you multiply that by 20. So let's do a little example here. Look at our picture, and let's figure out here, this pressure, 0.0002. If you put 0.002 and put that on top of 0.0002, so let's say you add a pressure, and I'm going to write it over here as well, 0.002 over 0.0002. Turn on my light here, stop sharing screen. There you go. So let's say I did that. Let's say I had a pressure of 0.002 over the softest that took you just barely here, 0.0002. What is that ratio? Get your calculator out and bank in 0.002 divided by 0.0002. What will you get? What's the ratio? What does it boil down to? And when you do that, you're going to get a number 10. Because 0.002 divided by 0.0002 equals 10. 10 over 1. So what's the logarithm of 10 over 1, or 10? Well, go to your book here. What's the logarithm of the number 10? All right, come on, make my PowerPoint work here. Oh boy, screen froze, but at any rate. There, what's the logarithm of 10? Go to the right, 1. In other words, in English, how many times does 10 have to be multiplied by itself to equal 10? 1. And then go to the third part of the formula. So you figured out the ratio. It was 10. 10 to 1. The logarithm of 10 to 1 is 1. And what's 20 times 1? 20. So here you go. What is this in terms of its sound pressure? Whoa, don't move that. Undo, undo. I don't want to do that. Move that back down here again. Okay, there you go. What's the logarithm of this ratio here? Or what is it in dBSPL? 20. Okay? In other words, when we put 0.002 as the sound pressure right here, if that was the pressure we had, then what is that in decibels? What is the decibels SPL of that pressure? What is the dBSPL of this sound pressure? It's 20. The graph shows it just visually, but the formula shows how we got there. You put 0.002 over 0.0002, you did the division, you got 10. What's the logarithm of the number 10? 1, and 20 times 1 is 20. And that's how we got from here to here. Okay, let's do 0.02. Let's put 0.02 as the top number here. So if you make that 0.02 divided by 0.0002, what will you get? You're going to get 100. And what's the logarithm of 100? Here, on this page. What's the logarithm of 100? 2. How many times did 10 have to be multiplied by 10 to equal 100? Twice. 10 times 10. Okay, now do the third part of the formula. What's 20 times 2? Because the logarithm of 100 was 2. So 20 times 2 is 40. So what was the dBSPL of this pressure? 40. Told you. So the purpose of this formula is to say, if I have X amount of pressure against my eardrum, what is the dBSPL? That was the purpose of this formula. You're trying to get from pressure to decibels, and that's how they did it. You take your whatever pressure it was against your eardrum, put it over top of the softest pressure it took to just barely hear the sound. And what was the ratio? What's the logarithm of that ratio? Multiply that logarithm by 20, and you got your dBSPL. So this formula right here is how, whoa, I don't want to do that. We'll move it back here. Okay, whoa, way too much there. Okay, so that formula over top of 0.002, okay, times the logarithm times 20. You've got the 3 parts to the formula. Basically, that's the thing to know. Now, when you work your way down the page, Okay? Don't go any further than this. By the time you get to here, right in your margin, okay, right on the side over here, FNO, for nerds only. Freak not out. Don't worry about it. It's there if you're a nerd and you really you like math and you want to get into it, go for it. I'm not covering it, okay? So leave it alone. What I want you to concentrate is right here. This is giving you two examples, and it's the two examples we just did. For example, the top one. If the pressure was 0.002 dynes per centimeter squared, you can see how we first did the ratio. We got 10. Then we did the logarithm of the ratio. We got 1. Then we did 20 times 1, and you got 20 dBSPL. A second example, if the pressure against your eardrum was 0.02 dynes per centimeter squared, you put that over 0.0002, you get 100. What's the logarithm of 100? 2. What's 20 times 2? 40. And so on. Okay? This verbiage here describes this. Okay? This verbiage here describes this. So on a quiz or on an exam, I may very well give you a question that says, calculate the dBSPL of 0.2 dynes per centimeter squared. And I'm going to ask you to tell me what that was in dBSPL, not by memorizing it. I want you to show the work. You'll put 0.2 over 0.0002. You'll get your calculator. You'll calculate what that ratio was. And you'll find out what the logarithm of that ratio is. Okay? Because this might be, 1,000. This might be, like 1,000 times the pressure of here. And it is. This is 10 times the pressure. This is 100 times the pressure. This is 1,000 times the pressure. What's the logarithm of 1,000? Well, how many times does 10 have to be multiplied by 10 to equal 1,000? 3 times. 10 times 10 is 100, times 10 is 1,000. What's the logarithm of 1,000 then? 3. And what's 20 times 3? 60. Okay? That's the extent to which, but you need to internalize this. The fact that the decibel uses logarithms on base 10, and it does that because the range of pressures is so huge that we don't feel like dealing with 1,000,000 increments. We'd much rather deal with 120 increments. It's way, as they say in the Deep South, mo better. Way mo better. Okay? Easier. So basically, when you're thinking about doing audiometry, and you're looking at your decibels on the audiogram, yeah, they all look like, oh, this is 10 and 50 and 20 and 70 and whatever, but realize that underneath, it's all based on logarithms. Anyway, the human ear is amazing because the softest it can tolerate is real, or that it can hear is really soft in terms of pressure. And the biggest pressure it can tolerate is 1,000,000 times the softest pressure. And we don't want to deal with that range of pressure in millions. We'd much rather call that range of pressure 0 and 120. Easier. Okay, we've come a good ways. We're just about done for the day. Looking at our notes here, we now get to the very bottom of the page, and I think we can generally call it a day. All right, so we're going to meet next week. We may complete this unit, maybe not. I think we probably will, because you've covered. This is a weird unit. This is acoustics. At any rate, this is the coverage of the decibel and amplitude of sound. Next week, we're going to look a little bit more at pressure ratios. In other words, we're going to look at what happens when you've increased the pressure 10 to 1, you went up 20. Here you go. This is a table of that same picture here. So just a table showing you 100 to 1, 40 dB SPL. You've increased the pressure 1,000 to 1, you went up to 60 dB SPL. Increased the pressure by 10,000 times, you've gone up to 80, and so on. So this table simply is this graph. Just hook them together. And next week we're really more going to focus on basically, if you double the sound pressure, does it double the dBs? We're going to be talking a little bit more about what happens if you have a machine making 85 decibels in one corner of the room, and you have another machine making 85 decibels in another corner of the room. How many decibels do you get when you add them together? Is it 85 plus 85? You know why? Because the decibel's based on frickin' logarithms. That's why. Let me give you a case of in common sense, and then we'll call it a day. Let's say you have a lady singing in a choir. A lady singing some church hymn or whatever, and she's singing at about 70 decibels, which isn't that loud. It's just kind of, about average. She's singing at 70. What happens if you have 10 ladies standing next to each? Are you going to have 70 times 10? Is it going to be 700 decibels? Hell no, my ears are going to bleed. Okay? It doesn't work that way. 10 ladies singing, okay, versus one lady singing is probably going to be about 80 decibels. And 100 people singing versus one person singing is probably about, if the one person singing at 70, 100 people singing is about 90. Okay? You can't just add them, multiply, and it's because the decibel is based on logarithms. And that's what we're going to be talking about next week. How do you make this make common sense if you're talking about the intensity of a choir or the intensity of 4 barbershop guys singing a quartet? What's the overall versus the one? Anyway, enough on that. I'm going to shut my face. I'll stop recording and live long and prosper, as Spock would have said on Star Trek. All right. Adios.
See you later.
All right.